So in this video, we hone in on how to use inverses to solve particular systems of linear equations. Remember, it has to be n equations and variables, or this you can't do any of this. So the first thing is an important theorem, which is the whole point of doing this, which is if you have a linear system where you have A is an invertible matrix, that's the coefficient matrix of the system, then the system represented by the equation AX equals B has one and only one solution, and it is this X equals A inverse times B. And that's true for every vector B in Rn. So doesn't matter what the constants are in B, you're always going to have a solution. It's always found by just multiplying B on the left by A inverse. That's fantastic. That's just a great result. That means we can solve systems very quickly if you just give me an inverse. Now, why it's true is also very easy. Looking at first, I've already shown you this part just with A prime notation. So then if you start with the equation AX equals B, by just multiplying on the left by A inverse and tracing through the algebra again, you get that the only possible solution is X equals A inverse times B. I now have to reverse those steps. That will then show you that if X equals A inverse times B, that it would be a solution. So that it's a possible solution and it's the only solution. So to do so, though, I will go ahead and just start off by saying, let's just say X is that thing. We'll look at the equation A times X and see what it becomes. You would then have A times X. That will then be just replace the X with what X equals. Then by reassociating, you then get the identity matrix times B, and that's B. So that means then that X equals A inverse times B is the only possible solution, and it is a solution. So therefore, it's the unique solution. That's it. That allows you then to go and solve systems if you only have the inverse. Unfortunately, to use this, though, you need to have an inverse. So we're going to work with a really simple case. That's this one. We're looking only at 2 by 2 matrices. Suppose that you have a matrix that's 2 by 2. Then A is invertible and the inverse is given by that formula. Amazing. If the particular product A times D minus B times C is just not 0. So as long as A times D minus B times C, which from now on we'll call the determinant of A. So we just call it the determinant of A is just going to be equal to that number. If the determinant of A, that particular product, is not 0, then the matrix is invertible. And not only is it invertible, I can tell you what it is. That's great. And then also, if it is 0, then A is actually not invertible. It has no inverse. So this is a fantastic result. It's an amazing result. It certainly deserves a proof. So before I do that, though, let's just use it real quick. Suppose you have this matrix. Notice that if you take the determinant, that'd be 5 times 3 minus -1 times 2. That's 17. The most important thing is just not 0. The minute it's not 0, that means that the matrix is invertible. And by just using the formula, notice you take the entries on the main diagonal, and all you do on that main diagonal is you would go and flip them. That's how to get these. And then whatever's on the off diagonal, you just take their off, you take their negations. So that's how I got the inverse. And out front, you just divide by the determinant. So then the inverse is given by this formula right here. So that's great. The minute we have the inverse, we can now use that inverse to solve systems of equations that have A as its coefficient matrix. Before we go do it, though, this is such an incredibly important result that it deserves explanation. So there's a couple things here. If it's invertible and the inverse is this thing, just because of the way it's written, it automatically implies that A times D minus B times C is not 0. So that happens instantly. This the other direction that's more important. What if A times D minus B times C is 0 or is not 0? If it is 0, I'm going to show you that A is not invertible. And if it is not 0, I'm going to prove to you what the inverse is. It's really straightforward. So what if you have that matrix and the determinant A times D minus B times C is not 0? Then all you got to do is write down the matrix I gave you for what I claim the inverse is, and just check, just take that matrix A and multiply it by my supposed inverse on left and right. And I just have to convince you that you get the identity both ways. And I'll leave you to do the algebra. I wrote it down all for you. Well, that's true. As long as A times D minus B times C is not 0, you are now able to at least divide by that number, and that's all you need. Everything else then carries through. So yeah, if it's not 0, the matrix is invertible. And I even tell you what the inverse is. That's great. The much, much, much harder one, which is more interesting, is that if it is 0, then it does not have an inverse. So the book gives you a way to argue this using systems. And since they gave you that argument, I'm not just leave it there. You can always read it. But I like doing things slightly different just because I want to connect ideas with what you've seen before. So this time, let's pretend that the determinant of this 2 by 2 matrix is 0. So A times D minus B times C is actually 0. There's actually two cases, two general cases. One case, all the numbers are 0. A, D, B, and C, they're actually all 0. The other case is the negation of that, which is at least one is not 0. So at least one of the letters is not 0. So let's handle each case. What if they're all 0? Well, that's easy, because if A, B, C, and D are all 0, then A is actually the 0 matrix. And we already know from what I just showed you that it just doesn't have an inverse. So we don't have to worry about that case. It's the second case. It's more fun. So as a second case, at least one of A, B, C, and D is non-zero. Without any loss of generality, the proof is extremely similar. If I choose any of the variables, I'll just pretend that A is not 0. Now in the column of the matrix, A and C are in the same column. So then take C and divide by the known non-zero thing, A. We call that K. You can do this now proof using the same idea with any of the letters. So B and D are in the same column. If D was not 0, I would define K to be B divided by D. And then the proof after that is pretty much everything the same. So then this, for now, just pretend that K is C times A. And let's just see where that goes. That would then mean that C is equal to A times K. But we know that since A times D minus B times C is 0, that implies then that A times D is actually equal to B times C. But we also know that A is not 0. So I can divide both sides by A to get D equals B times C divided by A. But we know what C divided by A is, it's K. So that means then that C is A times K and D is B times K. There are similar multiples of each other. Go look at the matrix then. If you go back to the matrix A, just replace C and D with what they're equal to. Notice that means that the second row is K times the first. So there are multiples. So the first row and the second row are actually multiples of each other. In the case where I assume that the determinant is 0 and A is actually not 0. Well, now let's go back to the argument I gave you before. Let's suppose for a minute that A actually was invertible. I'll show you that's impossible. If A was invertible, then look at the rows of this matrix. Well, since the rows of A are multiples, then by looking at row matrix multiplication, the rows of A times A inverse are also multiples of each other. And I'll leave the details of you thinking about it on your own. Just think about multiply this by A inverse on the side and think about row matrix multiplication. And you can see why there are multiples actually of K. On both. One's a multiple of K, the other. But by definition, A times A inverse has got to be the identity matrix. And none of those rows are multiples of each other. That's a contradiction. That's just not possible. So the assumption that A is invertible is just false. So now we know that if the determinant is 0, that the matrix cannot have an inverse. Let's recap it so you understand how we use it. Here is a linear system. It's a 2 by 2 coefficient matrix. That particular coefficient matrix, think of it in terms instead of matrix multiplication, and we use the inverse matrix to solve it. So we know the coefficient matrix is 5, 2, -1, 3. I just wrote down moments ago what the inverse was by using the theorem I just gave to you. But we also know from another theorem that the only solution to this system would then be X equals A inverse times B. And B here is 1 and 4. So the only solution is found by taking the inverse, multiplying it on the left of the vector 1, 4, and just doing that matrix multiplication. So that means then x here, that vector, is -5/17 and 21/17. So if you like, going back to the original variables, that means then that x equals -5/17 and y is 21/17. That's the original solution to the original problem. And it's the only one. It's the only one. So that's great. I think that's enough for that video.